So the idea of limits and continuity. And all a limit does is describes the behavior of a function. Okay? So the notation here, limit as x is approaching some value of the function. What is this function doing as x is approaching a? Right, so as it approaches a, what value does function x approach? Now, in the vast majority of cases, you can just substitute in because you just go, oh, well, that's the y value. But where you have a discontinuous curve, like your hyperbola, then it doesn't actually have a value at, say, 0, and you're interested to know, okay, well, what's it approaching? What's the curve doing as we're getting closer and closer? We can also, because if you look at the hyperbola over there, if we approach it from the left-hand side or the negative side, we would actually get a different answer to if we were approaching it from the positive side. So occasionally you'll see this notation. A with a negative means approaching A from the negative side. And so I've got the absolute value curve would be another example. Now, in this case, the limit of the absolute value of x minus 1 as x approaches 1 from the negative side is 0. As opposed to one of these split functions you sometimes see. If I approach it from the negative side, it would be 4. If I approach it from the right-hand side, well, the absolute value curve, it's the same answer. It's also 0. Whereas my split function over there from the right-hand side is not actually equaling 6, of course, because you'll notice the open circle, but it's getting closer and closer to 6. And that's where continuity comes in. If those limits are the same, then we know the curve's continuous. Whereas if they're different, we know it's not. So if those limits are equal, then we know it's continuous. Now, the reality of our course is that they don't really ask us questions about the plus and the minus. They usually just ask for straight limits. And as far as continuous, if they want to know, it's really a matter of looking at the picture and saying, oh yeah, this is continuous or this isn't continuous. So how do we find the straight up limits? Let's say the easiest way is to substitute in directly. In the vast majority of cases, we'll get an answer, and that's the limit. So we've got the straight line there, x plus 7. As x approaches 5, that would approach 12. Nice and easy. Doesn't always work, of course. One technique which is often useful, factorize and cancel. Because the problem we get a lot of the times is we end up with this 0 on 0 situation. If I was to sub 3 into this one, 0 on 0, well, what's that equal to? I mean, 0 on 0, we say anything on top of itself is 1, so maybe it's 1, but then we say, well, if you get 0 on the top of the fraction, it's 0, so maybe it's 0. But then we say, if you got 0 on the bottom of the fraction, it's undefined. Or infinity, sometimes we think of it. So what is it? If I factorize and cancel, we'll actually see it's none of those. Because now the x minus 3's will cancel. Sub into x plus 3, and the answer for this is actually 6. So it wasn't any of those three things. 3 plus 7 is... 6 is the correct answer, though. I did a cut and... I see, I did a cut and paste, but didn't change the 7. All right. Now... we need to introduce a special limit, because one of the things we're really interested in graphs is what happens out at the endpoints, so out at infinity. And so in order to do that, we look at one graph we know for sure, the hyperbola. And we know if we've got that reciprocal graph, the one on x, out at infinity, that's getting closer and closer to the axis. So we know the limit would be 0. If it was possible to reach infinity, the answer would be 0. And then we can use that to find the limit of something like this. What I do is I divide everything by the highest power. So every single term, the highest power there is x cubed. So I divide everything by the highest power, and then I can do some cancelling, and I now have a situation where I'm substituting infinity into the bottom of the fraction. But our special limit tells us that, hey, when we substitute it into the bottom of the fraction, it's going to be 0. So every one of those fractions will be 0. And I'm just left with a quarter. Now, there is a quicker way of doing that, of course. And that's by just looking at it. If I know I'm going to divide everything by the highest power, all I've got to do is look at the coefficients of the highest power. That's going to end up being my answer. So if I had one like this, limit as x approaches infinity of 4x minus x squared on x cubed plus 1. Highest power is x cubed, so that's the only coefficient that's going to be left. So I would be left with 0 on 1. The limit of that particular one must be 0. Highest power in this one, 7. Again, just look at the coefficients of x to the power of 7, and we know the limit of that one is a third. The other way, I guess you could do it, is via a polynomial division. And sometimes, if it happens to be, because what you're really doing is finding the horizontal asymptote of these graphs. And as we saw earlier, when you do a polynomial division, the number by itself out the front there turns out to be the horizontal asymptote. So that's another way you could do it. However, when you get ones like this, it's not going to be a horizontal asymptote. It'd actually be an oblique asymptote when you do the division. Because look what happens. If you look at the highest power, I end up with 1 over 0, which is undefined. So this must be approaching infinity. Okay? So it just keeps going up. As I say, we can use it to find horizontal asymptotes. If we don't want to do the polynomial division, and it's fine so long as we don't get the situation of 1 on 0, it'll find the horizontal asymptote for me. Highest power is x squared there, so it must be 1 for this one. So it is possible to find it without doing the polynomial division. All right, so 7i's just got a few questions there on playing with this idea of limits.